Hi, Bruce Rouse here from the Sustainability Education Academy. Today to talk about ideas on overcoming challenges with using heat pumps to replace gas systems for providing heating, space heating in buildings. So the reason I'm calling this a webinar ideas is because I'm putting forward some ideas, but I'm really interested in your ideas as well and your feedback. So I'm calling them ideas rather than solutions. Um, so let's just get straight into it. So basically, we have with different gas systems, we basically have, um, I guess you could say, four different types of systems. We can either have a gas furnace, which basically just heats air, and that gas furnace is located in the room. We could have a gas furnace which is ducted then with air ducted into the room. Maybe that gas furnace would supply multiple rooms. A fourth possible configuration is where we have a gas boiler that supplies heating hot water to air handling units or fan coil units. Basically just radiators with air flowing over them. And then finally, we could have a gas boiler supplying heating hot water to a room mounted radiator. They're the main ones. Of course, there's others, perhaps hydronic heating, underfloor slab, stuff like that. But let's just focus on these four, which are typically the ones that you find in commercial buildings. And I guess I've got more of a commercial building focus here. So, what are the challenges? Um, so, the challenges would include a low temperature heat or delta T. So, let me just explain. A gas boiler will typically provide heating at around about 80 degrees C for a boiler. For a furnace, I'm not quite sure. It's around, it can't be too hot, otherwise it's going to burn people if you stroke it. It's pretty warm and mixes with the air, so possibly 35, 40 degrees. I really don't know. For those of you who work in this space more closely, might be able to advise that exact temperature. Um, so an in-room gas furnace, if you replace it with a heat pump, um, look, you may not get the same temperature with a heat pump, but you can get pretty high, and it's probably not much of an issue, not much of a challenge. Ducted gas furnace, well, then you may be running hotter temperatures in because you're relying on mixing of the air. But again, I think that you could probably use a split system to replace the gas furnace uh, and a ducted gas furnace. Okay, gas boiler supplying heating water. Now, this is a problem. Typically, heating hot water is supplied at 75 to 80 degrees Celsius. Typically, a heat pump is going to be producing just a standard heat pump at about 45 degrees Celsius, maybe 50. Um, so there's a big difference there. And because of the lower temperature, uh, um, you're not going to generate as much useful heat from that fan coil. You're not rehandling it. So that's a problem. Um, Heating hot water to a radiator, yeah, typically radiators are supplied with pretty hot water as well, and that could be a problem as well. Now, it won't necessarily be a problem when the load is light on the system, or when you've got a heavy heating load, then it's going to be a problem. Okay, electricity supply. Okay, yes, you put in a split system, it's always going to use more electricity than the fan on a furnace or the burner, um, and pumps uh, associated, or the burner associated with a boiler, um, and any fans. So yes, you're going to need more electricity. Possibly, depending on the extent of the upgrade, you need to upgrade the electricity supply. So that could be a problem. Typically, when you're placing large boilers, yes, that is definitely a problem with the electricity supply. Will need to be upgraded. So that's a challenge for all systems. Space constraints. Yeah, okay. So typically we have space constraints. Um, Not so much in an in-room gas furnace. Often there's lots of room on the wall for, let's say, a split system. For a ducted gas furnace, space might start to become more of an issue. But for a given amount of kind of heat energy, a heat pump will be bigger than a boiler. And so we're perhaps starting to get problems here with lack of space in plant rooms when we've got gas boilers or even gas duct furnaces. Additionally, we need space for the outdoor unit, or in a heat pump, it's not actually the evaporator. It's not actually the condenser, it's the evaporator, but it's the outdoor unit. You need space for that as well, and you've got to run extra pipes there. So there's certainly space challenges. With most systems, probably the in-room gas furnace is the one with the least space challenges. Well, you've still got to find space for the outdoor unit. Okay, cost to benefit ratio. Now, the reason this has got a star is that it depends obviously on the electricity tariff. uh, versus the gas tariff. Um, so if you have a cheap electricity tariff and a high gas tariff, well, then the cost benefit of an upgrade will be better. Um, uh, in general, though, it's also going to depend on the coefficient of performance of the system. So a COP, um, let's say a system with a higher COP, like a split system, where the temperature is relatively low of the heat, um, will it have a higher COP than say a system which you're maybe say using a two-stage heat pump to get your water temperature say up to 75 degrees Celsius. So then yeah, the COP will be lower, which means you need more electricity to produce the same amount of heat. So therefore the cost benefit drops. So again, we kind of get as we come across here, particularly with this gas boiler situation, that becomes more of a challenge. Higher carbon emissions in a grid with a dirty electricity. Yeah, basically, natural gas is relatively clean compared with, say, coal-fired generated electricity. Um, so we're needing um, a pretty clean energy source, um, electricity source, in order for this to make sense. So typically, we need um, very clean grids for the emissions savings to make sense. Now, just sort of a couple more comments here before I get into some of the ideas. So, the heat pump efficiency, or COP, is inversely proportional to the delta T. So that's the temperature difference between the evaporator and condenser. The bigger that is, the lower the COP, the lower efficiency of the heat pump. And so clearly, we want to keep the output temperature as low as possible, um, in order to get a higher COP. The higher we go, the worse the COP. Now, also, the bigger the evaporator and the condenser we can build, when we get a bigger evaporator, bigger condenser, basically we can get away with a lower delta T between the refrigerant on the inside of the evaporator, or the condenser in this case, and let's say it's an air system and the air. You get a lower delta T. The bigger the condenser, and therefore with a lower delta T, we can be generating, um, I guess, either more heat, a high temperature air if it's a furnace type situation, or we just need a more space. So this space constraints the issue. So here's some ideas. So firstly, the idea is reduce the need for heating, because this upgrade could be challenged. So this involves building ceiling, insulation, better windows, heat recovery. Um, I just want to touch on the one with better windows. Now, in many climates in winter, windows are useful if they're facing kind of the direction the sun is at. It's either north in the southern hemisphere, or if they're facing south in the northern hemisphere. Um, you can get quite good radiant heat gain through those windows. So, but you want to be keeping that heat in. So there's some surface treatments on the windows, like a low emissivity coating, to keep the heat in. The other things we can do is we can assess peak thermal loads. So the existing gas equipment could be oversized. And if it is oversized, we need to understand it if it is. So we need to really assess those thermal loads, do some thermal metering, to understand the thermal loads on the system. And then if once we understand those peak thermal loads, which is what the system needs to be sized for, we can look at strategies to reduce that. So could we have a longer warm-up period to reduce the peak loading, or a system that may be really struggling on a cold morning, just give it a bit more time to get the building up to temperature? Can we use some thermal mass to lower peak loads? Look, in my house, I've got a stack of thermal mass, and I get good radiant sun, which comes into my house. It's kind of designed that way to get that radiant sun in winter. And in actual fact, that actually does um, reduce the loading on my heating system, because the house actually never gets super, super cold. It never really drops much below about 13 degrees Celsius, when the outside might be 3 or 4 degrees Celsius. So, and that's because of that thermal mass. Now, so I don't need as much energy, peak load, I guess, to be able to heat the house, although I do need to run for longer, given the thermal mass absorbs a lot of heat. Another suggestion would be to change the system type. Now, this is just when there's a major upgrade that happens. So typically, if you've got a boiler-based system, and that system's at the end of its life, maybe you could look to going to a VRV, variable refrigerant volume system, or switch from a hot air, a boiler-based system with air handling units to maybe a ducted, split ducted, or split systems like a VRV system. So that way we can have a lower temperature to deliver the same amount of comfort. Um, so we're coming back to these understanding here that we need a delta T is kind of our enemy, a high delta T. So we want to reduce that delta T if we possible. And we showed here that split systems tend to have can operate with a lower delta T and still provide comfort. There's a little bit more air in the room. Okay, so that's how we can perhaps change the system type. So these are some of the ideas of some of the challenges. Um, and I'm not necessarily addressing it if you can't reduce the need for heating, if you can't reduce peak thermal loads, well then you've got a problem. And if you can't change the system type, well then you've got a real problem with a changeover. So you need to think a bit out of the box. And I need to say that when you're doing this sort of upgrade, you do need some good knowledge of HVAC, and it's really an engineered solution that needs a fair bit of thought. And in just saying that, if you're not quite sure about what to do, I just want to bring to your attention some courses on the Sustainability Education Academy, one of which is the fundamentals of energy efficient HVAC. So this certainly addresses that, getting that understanding around HVAC, and it's got a pretty comprehensive course. We cover heating, cooling, heating, the vapor compression cycle, which you really need to understand if you're going to be specifying heat pumps. Cooling, air movement, evaporation, ventilation, filtration, air handling, conditioning, distribution systems again. And this comes, you really need to understand this when you're doing heat pump upgrades on their systems, fans and pumps, control systems, and HVAC opportunity analysis. And finally, some practical guidance on HVAC upgrades. So this is a super useful course if you're planning to do a conversion of a system to heat pumps. So I hope this was useful. And if you've got any ideas, just please drop a comment. That would be great. Okay, thanks.